We've all heard of black holes, and thanks to our telescopes, we have solid evidence of their existence. But what about their theoretical opposites? What exactly are white holes, and more importantly, could they actually exist? White holes are purely hypothetical objects, born from the minds of physicists. While they might be possible, we have yet to observe any direct evidence of their existence, or even a hint that they could be real. In essence, they are the mirror image of black holes. Nothing can fall into a white hole, but everything inside must come out. Unlike black holes, which trap everything within their event horizons, white holes remain an intriguing yet entirely theoretical concept. Astronomers have never identified an object that could be classified as a white hole. So why do scientists even consider their existence? The answer lies in the work of Albert Einstein. Even though we haven't detected white holes in our universe, the idea that every black hole might have a corresponding white hole on the other end isn't entirely unreasonable. To better grasp this concept, we must revisit the foundation of modern physics. Einstein's field equations predict the formation of black holes, but surprisingly, those same equations also allow for the existence of white holes. Could they be real? If so, where are they hiding? How did we uncover the nature of black holes? While most of our knowledge about black holes is relatively new, the concept itself has deep historical roots. The idea of an object so dense that it traps light and becomes invisible to the rest of the universe was first proposed in the 18th century by natural philosophers Jean Michel and later Pierre-Simon Laplace. Michel referred to them as dark stars, after Albert Einstein introduced his general theory of relativity. In 1915, German physicist Karl Schwarzschild and Dutch mathematician Johannes Droste began exploring the mathematical foundations of these mysterious objects. At the time, black holes were seen as little more than a mathematical curiosity. Schwarzschild's equations predicted the existence of a critical boundary around such an object, what we now call the Schwarzschild radius, beyond which nothing, not even light, could escape. If our sun were to collapse into a black hole, it would shrink from its current 1.4 million kilometer diameter to a mere 6 kilometers. Within this minuscule radius, its average density would skyrocket to around 20 billion tons per cubic centimeter. At the time, directly observing such phenomena was virtually impossible. However, the mathematics suggested something extraordinary. Space behaved just as Einstein's equations predicted, until extreme gravitational forces came into play. When a massive star exhausted its fuel and collapsed inward, gravity would grow infinitely strong, causing space itself to fold in on itself. This led to what we now call a Schwarzschild singularity, where the very fabric of space and time loses all conventional meaning. In 1958, American physicist David Finkelstein was the first to recognize the true nature of black holes, describing them as one-way membranes through which nothing could return. Then, in 1963, mathematician Roy Kerr solved the equations for rotating black holes, revealing solutions that implied the possibility of closed time-like curves, essentially allowing for theoretical backward time travel. Even earlier, in 1949, logician Kurt Gödel had explored similar strange solutions within Einstein's equations, further highlighting the mind-bending implications of black holes. White holes are theoretical cosmic regions that function as the exact opposite of black holes. Just as nothing can escape from a black hole, nothing can enter a white hole. While space-time flows inward toward a black hole, it flows outward from a white hole. The term black hole was first introduced in 1964 by American journalist Anne Ewing and theoretical physicist John Wheeler. A year later, in 1965, Russian theoretical astrophysicist Igor Novikov coined the term white hole as its counterpart. Novikov proposed that if the universe contained regions with certain properties, then there should also exist regions with precisely opposite properties. A black hole is a region of space with an immense gravitational pull, trapping everything that crosses its event horizon. Nothing, not even light, can resist its grip. In contrast, a white hole would act in the reverse manner. If something were to fall into a black hole, it might eventually be expelled back into our universe through a white hole. In this sense, a white hole can be thought of as a black hole running in reverse time. Black holes and wormholes arise as special solutions to Einstein's equations when space-time is intensely warped by gravity. This idea is closely linked to the mathematical concept of the Einstein-Rosen bridge. First, mathematically, discovered in 1916 by Austrian physicist Ludwig Flamm, and later revived in 1935 by Einstein and American-Israeli physicist Nathan Rosen, this bridge would eventually become known as a wormhole. Wormholes are theorized to act as shortcuts between distant points in space-time. Imagine two towns on opposite sides of a mountain. Normally, travelers would have to take a long route around the mountain to visit each other. However, if they could dig a tunnel straight through, their journey would be much shorter. This is the fundamental concept behind a wormhole, an interstellar shortcut that could potentially connect two vastly distant locations in the universe. Are white holes possible? Unsurprisingly, the idea of entering a black hole portal and reappearing somewhere else in the universe, whether in space or time, has inspired countless science fiction stories, including Doctor Who, Stargate, and Fringe. Mathematically, white holes seem possible. However, there is no physical evidence to support their existence. While mathematics can outline what could happen, only observations, measurements, and experiments can confirm what does happen in the universe. White holes remain unlikely because they require a reversed process. As far as we can observe and measure, time in our universe flows in only one direction: forward. One thing is certain: black holes will continue to intrigue and mystify us for a long time. Meanwhile, white holes will remain an interesting theoretical possibility, but for now, they exist only in the realm of speculation. Thank you for watching and for sharing your time with me. I hope you found this journey through black holes and white holes as fascinating as I did. If you enjoyed this video, don't forget to like, comment, and subscribe for more mind-bending space mysteries. Until next time, take care and stay curious.